Hi, I'm Klaus Gessner, the Chief Geoscientist of the Geological Survey of Western Australia, GSWA, and today I will talk about the Geoscience Strategy. The Geoscience Strategy was developed as part of the long-term strategic priorities of GSWA. Above all that sits the overarching GSWA Unearthing Western Australia strategy, and others form part of that. For instance, the Geoscience Data Transformation Strategy that was published last year, and the Stakeholder Engagement Strategy, which is still to be published in the future. So part of that is the Geoscience Strategy, and the purpose of that is to provide a guiding framework for geoscientific activities within GSWA. Now, there are all kinds of activities in GSWA, and geoscience is a part of that. So specifically, it covers the geoscientific activities within the survey. There are really 4 parts to the geoscience strategy and also to the presentation that I'm giving today about it. And the first one is the mission and the terms of reference, which gives an overview on what we want to achieve and what it is that the geoscience strategy covers. We then move on to a review section where we look at an environment analysis. Where do we fit and what do other organizations do that have a similar remit? We then move on into the enabling steps. What's really required to fulfill our mission? And this is what I call integrated geoscience, and we'll talk about an Earth systems approach to understanding what Earth basically. The other part of the enabling steps is how we can manage the expectation and measure success of the actions that we are undertaking, the activities we are undertaking. And this talks about input, output, and outcome, understanding the value chain, if you like, of knowledge generation and management. And then we will break down the activities that the survey is planning to do or should do in the future. And the key of that, of course, is understanding the geology of Western Australia and its Earth resource potential. Another important point here is knowledge integration, and we'll talk about that as well. Let's start with the mission and the terms of reference. Let's start with the terms of reference. For the purpose of this strategy, we define geoscientific activity as the rigorous acquisition and verification of knowledge of the Earth system through observation, analysis, and hypothesis testing. Our mission is to unravel WA geology and Earth resources, really understand how the geology formed, how the resources formed, and how the two are related. We do that by attracting, developing, and retaining highly skilled staff for data acquisition, analysis, and production of outcomes. So this has to be state of the art, both the acquisition, the analysis, and the interpretation techniques. We gather the data and from it derive information and knowledge products. We do that to stimulate the mineral and energy sectors of WA that will then benefit the WA community and economy. But also it does support or sustain technology-supported human development globally by feeding raw materials into the value chain. So basically, we like to provide knowledge-based information to government, scientific community, industry, the public, on all matters related to solid Earth in Western Australia. So what is the environment we operate in? How do we fit in globally or nationally in what's happening with Earth sciences? Let's start with the big picture. Where are we? We are in the 21st century, and so we live in a world that has the lowest level of poverty, illiteracy, famine, child mortality, and death by war, tribal violence, that humankind ever experienced. If you look at those two graphs, 1970 and 2021, these are graphs that show the distribution of income around the world, it's not so important to look at the individual colors. In this case, red is Asia, green, think North America and South America, yellow, Europe, and blue is Africa. But if you look at the 1970 graph, it shows basically a bimodal distribution where a large part of the global population, 45%, lives in extreme poverty. And this has changed quite a bit. In 2021, even though, of course, there's plenty more people on the planet, right? The pattern changed from a humpback to a shark fin, almost in curve, but now only 10% of global population live in extreme poverty. And this is a success story that is fueled by industrialization. So the mineral and energy sectors have contributed as the foundation to that success. And we often think about transport or mobile phones and things like that, but think about healthcare, pharmaceuticals, housing, agriculture, and all of that is underpinned by industrialization, and industrialization is underpinned by the production of affordable minerals and energy. Now, climate change is a big challenge for us in the future. There's no question about that. But, because we don't want to throw away the achievements of civilization, of human development, we have to manage our resources carefully. And to do that, understanding the Earth is fundamental. It's a fundamental requirement to human development. Of organizations have produced strategic documents over the last few years, including the International Energy Agency, which has laid out a roadmap to net zero by 2050. So basically a net zero carbon emission economy by the year 2050. But there are other documents as well that are worth considering. That is reviews on critical minerals in Australia and what the opportunities and research needs are for these, but also how Australian resources can provide prosperity for future generations. This is the Resources 2030 Task Force report. Another interesting document is the Decadal Plan for Australian Geoscience that was published in 2018 called Our Planet, Australia's Food Future. And it lays out the requirements for academia and government, how the national needs for geoscience can be met. Another important document really is the Amira Uncover Australia document, which talked about unlocking Australia's hidden potential. And here the focus is clearly on the mineral sectors and how resources that are covered by regolith and sedimentary basins can be explored for and exploited in the future. So clearly there are plenty of challenges for geoscientists for the future. So how can we do this? How can we tackle these challenges, understanding the Earth to ensure that we can supply affordable and clean energy and support human development in the future? So one way of doing this is to understand the Earth as a system. One way to look at the Earth is to look at what it's made of. And this is rocks and minerals. So trying to understand the material, the composition, and the structure, and preferably both. So this helps us to say, what is it? What rock is it? What mineral is it? So basically, it's a characterization of the solid Earth. And we've actually done this since a long time, probably since the Paleolithic, when people were reliant on understanding Earth materials as the most modern tool at the time. In addition to understanding the material, what kind of rocks we look at, it's also important to understand the dimensions of time and space. So where and how big is a certain geological formation? how long, how deep, how wide is a geological structure in 2 or 3 dimensions. And in terms of time, the question is, when did things happen and how long did they take? From this came mapping and stratigraphy, and we've done that since the times of the Enlightenment, probably. As an example, Charles Lyell formalizing stratigraphy, that's a great example. So the dimensions of time and space are another way of looking at Earth. Component is process. Here we try to understand how exactly does it work? How does Earth work? And to understand this, we have to understand how physical processes operate and how they're coupled. So these are heat flow, fluid flow, chemical reaction, transport of chemical species, and rock deformation. They're all part of the puzzle. They all interact. And to understand the interaction of these processes is essential when we're looking at trying to predict Earth systems, try to predict the stability of a civil engineering structure, or trying to understand the heat production or the energy production from a geothermal system. If we don't have a basic understanding of process interaction, this is not possible. And this is something that happened quite recently in earth sciences, when earth sciences moved from being descriptive into becoming predictive. And in fact, Australian scientists, for instance, Bruce Hobbs and Alison Ord as an example here, have made a massive contribution to that. To understand any geological system and to define it, we have to understand the interaction between material, dimension, and process. Otherwise, our understanding is not complete. For instance, just looking at heat flow and fluid flow, not considering the composition and structure of the rock they act on, will not help us to understand how a big ore body forms, or how regolith forms, or why a volcano erupts in a certain way. So how do we apply our geological knowledge, our geoscience knowledge, to our work at the Geological Survey? At the beginning, there's always the data that we acquire or obtain. We might purchase it from a service provider, we might collect it by mapping or by operating a piece of lab equipment. We process it and we analyze it. This is the data stage. Then the next stage in the knowledge chain is to turn the data into information by providing relevance and context, putting into a spatial context with other samples, for instance. With the experience and knowledge we have, the corporate knowledge in our organization, we are then able to add significance to it and turn it into a knowledge product, such as a geological report, a GSWA record, or paper. All of this is the management of knowledge, turning data into information and knowledge, and then having the knowledge feed back into decision making in terms of what knowledge to apply and how to turn the data into information and which data to acquire in the first place. That is all part of the workflow in the survey. In addition to knowledge management, there is also data management. This involves the storage and delivery of that knowledge into products. Let's talk about knowledge management in a bit more detail. GSWA's organizational knowledge is an important asset. It resides in our people and in our products. We need to communicate it, store it, and make it accessible and updatable for it to be significant. In the future, it may also need to be machine readable. So we go from a traditional knowledge transfer from sitting around the campfire to a way of encoding geological history in a machine readable format, such as shown in the Loop 3D project. It's worth considering how activities lead to impact. When we plan work in our organization, we can really only control the output by the decision we make how to carry out our activities. Whereas we also hope for a positive outcome and an even more positive impact. So it's really worth keeping in mind that when we want to contribute to the WA economy, what kind of outputs do we generate that will produce or influence people to make a decision that will be beneficial to the state? So what activities exactly do we want to undertake in the future? How can we break down the activities in different streams? Fundamental to understanding the geology of WA is understanding the thermomechanical and chemical evolution of the crust and mantle, and how individual components of WA interact and what kind of boundaries they have. So we need to image lithospheric building blocks and crustal architecture. We need to understand basin evolution. We need to understand regolith landform evolution and the role of the biosphere in Earth systems. 3 examples of large-scale data sets that we continually will improve. This is, for instance, isotopic mapping as an example here, samarium, neodymium across the state, or trace elements as an example here, granites in the Yilgarn Craton, or moho depth, where we'll now undertake the WA Array project, 10-year project to map crustal architecture and lithospheric architecture in Western Australia using passive seismic. Planning the large scale sometimes requires data acquisition at the small scale. For instance, in zircon geochronology, the mapping of metamorphic minerals using TEMA, or undertaking macro and micropaleontological studies. In the end, it is the field work that generates the spatial context for the observations and brings everything together. Of our activity is understanding WA's Earth resource potential. But system study will focus on constraining the temporal evolution of mineralizing events and mapping distal footprints. Petroleum and energy systems work will focus on source rocks for hydrocarbons, but also seal and reservoir studies for geothermal energy, carbon capture and storage, and for hydrogen production and storage in the state. The integration and management of knowledge also is an important scientific undertaking. This means we need to manage our physical assets, such as rock samples, fossils, and the cores in our core libraries. We need to develop our observational and stratigraphic databases and to encode and integrate information and knowledge. We also need to automate prospectivity and analysis and 3D modeling. To achieve our aims and objectives, we need staff that operates at a very high technical level. We need to be able to attract them, to develop them, and to retain them. Some of the work we undertake also requires scientific collaboration, and we have been doing that successfully with a number of universities and labs around the world. So understanding the solid Earth in WA requires substantial advance in imaging and computing capabilities in the future, and in a better understanding of Earth processes. We are facing the transition to a low carbon economy. This means that we have to systematically explore sedimentary reservoirs. We have to explore for natural hydrogen, and we need scientific advances in the battery minerals value chain. Understanding and promoting the geology of WA is a fundamental part of an impact chain that generates economic benefits to the state. The scientific activities in GSWA need to be planned with a view towards that impact, but it all means that we need to get, have, and keep the right people to do it. To wrap up, I think there are challenging times ahead, but we have a great team and a unique opportunity to make a difference, not just to the WA community, but also to prosperity and to earth science globally. At this point, I'd like to acknowledge many colleagues who've provided lots of input, but particularly Simon Johnson and David Howard. And to all of you, thanks for listening.